Hello, my name is Matteo Galosci, and I'm here to present my lab for magnetic braking with Faraday's law. The purpose of this experiment was to observe the interaction of a falling bar magnet through an aluminum foil-based tube. After obtaining the physical results, we modeled the interaction computationally and compared physical and computational results by applying Faraday's law. The falling bar magnet is a source of external magnetic field which induces actually a current on the tube that applies a force on the magnet. Thus, we call this lab braking with Faraday's law. Some of the fundamental principles involved in this law was the Biot-Savart law, which outlines the relationship to magnetic field, to magnitude, direction, length, and proximity to an electric current. In addition to Faraday's law, which states that a magnetic field that is changing has the ability to induce a current in surrounding objects, like the bar magnet does on the tube, in which the tube puts a force on the bar magnet. Lenz's law shows that the magnetic field created by the induced current opposes the changes in the initial magnetic field, or the change in flux. In addition to these fundamental principles, we have the main fundamental principles of Newton's laws, second and third, which states that Newton's net force is equal to mass times acceleration, and each force contains an equal and opposite reaction force. So the experiment involved the use of a smartphone magnetometer app to determine the north end of the bar magnet. A tube of aluminum sits vertically while the magnet drops straight through it. Using our smartphone, we record the fall of the magnet with the camera and find the exact time the magnet leaves the tube as we scrub through. After 5 trials, the average for my physical model time is 1.68 seconds, while my computational time is actually 3.905 seconds. And I'll explain the difference in a little bit later. So after, going to my computational model, what I first did was I created a tube of aluminum foil. Then I created a bar magnet. Then I was able to create a function to calculate the magnetic field of the bar magnet while also creating a function to calculate its magnetic flux. My step 4 was actually the simulation step, where I was able to drop down the aluminum foil tube and create a chart that outlined the fall of the magnet with its velocity and the time it took to leave the tube. For a full link to my code, you can click the Here button. Here are my results of the computation model. On your left, you see a aluminum foil tube in gray, where with the north and south ends of the bar magnet in red and blue. And that red and blue, if you run the code, will actually fall down the tube. And on your right is the velocity versus time graph, where it outputs the time the magnet spent in the tube, and in this case it was 3.905 seconds. So the intensity of the coloring on the tube indicates the magnitude of current flow through each ring. Red and blue indicate the currents flowing in opposite directions. Red explains that red is the color of where it's saying counterclockwise, while blue is the color of clockwise. Using Lenz's law, the induced current will flow in the direction where the magnetic field will actually oppose the direction of the change in flux. Now, what happens to the dynamics of the system when you flip the magnet around? The induced current actually just runs in the opposite direction as before. The magnitude of the magnetic field always stays the same. How does the total time in the tube of your real world system compare to that of your computational system? Oh, in real life, the magnet has to fall a lot quicker, which is what our results also indicated. And then, in addition to the carbon inside the aluminum tube must be accounted for, as it does prevent some of the current from driving the magnet, or I should say braking the magnet. The shape of the velocity versus time plot tells, what does that tell us about the forces acting on the magnet? While in the tube, the velocity is actually constant, meaning acceleration is 0, and the forces on the magnet at that time are also constant. While not in the tube, the velocity has a negative slope, meaning the forces are increasing in the negative direction. Velocity is always negative, signifying that the downwards force of gravity is stronger than the upwards force, that is the magnetic force. Now, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Honestly, in reality, the magnet would fall less quickly through the tube as the resistance decreases, since the magnet could not fall through the tube because the force would be closer to gravity and would make the magnet get stuck in the tube, as the forces would actually oppose each other. Using that fundamental law that we always must remember, I is equal to EMF over R. Now, for the last question, what if the holes or slots were cut into the tube? How would this actually affect the ring currents in your model? Less aluminum, if we had holes or cuts in the aluminum, that means less aluminum to create an induced current on the magnet. Thus, less current, less force, the magnet will actually fall faster instead of having the braking effect as it usually does. Thank you for listening. Bye.